Can you imagine a place in the world where, by building just one hydropower station, you could completely solve 1/3 of Africa's electricity shortage? Its power generation capacity is a full 2 times that of China's Three Gorges. Damn! This genius project, which has made Western countries drool for 60 years, but none of them dared to touch, is now a blueprint so extreme that only Chinese construction teams dare to take it on. What kind of insane project is this? Exactly. Today we're going to talk about one of the most seriously underestimated rivers in the world, the Congo River. From the perspective of hydropower potential, it is truly the king of Earth's energy. The data doesn't lie. The Congo River is the world's second largest river, with over 41,000 cubic meters of water flowing through it every second. That is equivalent to every bathtub in a medium-sized city being emptied at the exact same time. Every single second. Near the lower reaches of the river, close to the ocean, there is a place called the Inga Falls. When the river reaches this point, it is suddenly forced into a narrow gorge and drops sharply. Millions of years of geological movement have turned this river into a natural hydraulic engine. The natural drop at Inga Falls alone is about 300 feet, roughly the height of a 30-story building. What is most remarkable is that most rivers slow down and widen as they approach the sea. But the Congo River does the opposite. At Inga, it narrows, accelerates, and becomes highly concentrated. This leads to a shocking geological fact. In theory, this single location at Inga Falls alone holds the potential for nearly 1/3 of all installed power capacity in Africa. Moreover, the Congo River is the deepest river in the world, with certain sections exceeding 700 feet in depth, enough to completely submerge a 60-story skyscraper. Such depth creates enormous water pressure and an extremely stable base flow. Even during dry seasons, its discharge does not fluctuate dramatically. All these conditions combined make Inga Falls one of the highest hydropower energy density locations on Earth. If you ranked all hydropower stations in the world by annual electricity generation, the top 5 combined would still not fully utilize the Congo River's potential. It is like a massive natural super battery buried right in the center of a continent. Unfortunately, for a full 60 years, no one has truly had the capability to connect the wires to it. When talking about mega hydropower stations, we have to mention China's Three Gorges Dam. The Three Gorges Dam on the Yangtze River has an installed capacity of 22,500 megawatts, enough to power the entire country of Australia around the clock. To build it, China officially started construction in 1992 and completed full operation of all units in 2012, nearly 20 years in total. During this period, more than 1 million people were relocated, and the flooded area was roughly the size of Singapore. The direct cost of the project exceeded $60 billion, and with supporting infrastructure, the total expenditure more than doubled. When the Three Gorges Dam was finally completed, engineers around the world agreed on one thing: it was the largest power station in human history, and it would not be surpassed anytime soon. In physics terms, the massive redistribution of mass after the reservoir was filled slightly changed Earth's mass distribution, leading to a measurable change in Earth's rotation speed, lengthening the day by about 0.06 microseconds. In China, the Three Gorges project is not just a power plant. It fundamentally reshaped the electricity supply and demand balance across central, eastern, and southern China. Alongside it, more than 5,000 kilometers of high-voltage transmission lines were built, carrying electricity from Hebei to Jiangsu, Shanghai, and Guangdong. In a sense, the Three Gorges project forged China's elite engineering force, capable of designing, building, and operating ultra-high voltage cross-regional transmission networks. And now that very force has arrived on the banks of the Congo River. Because the Grand Inga Hydropower Project is designed for a staggering output of 40,000 megawatts. That is roughly twice the capacity of the Three Gorges dam, literally blowing the ceiling off human engineering. So with a mega project this large, how much land would be flooded? How many people would need to be relocated? This is where the Grand Inga Hydropower Project becomes truly mind-blowing. Its fundamental logic is completely different from the Three Gorges Dam. The Three Gorges Dam is built by spanning the river with a massive wall, creating a huge artificial reservoir, and with it, enormous environmental and social costs. That is the classic cost structure of traditional dam engineering. But Grand Inga doesn't work that way. Inga Falls already provides a natural drop of about 300 feet. So instead of building a massive wall to hold back water, engineers can simply dig canals and tunnels to guide the water into high-speed turbines. You don't need to flood vast rainforests, and you don't need to relocate millions of people. The water flows in, passes through, and continues toward the Atlantic Ocean. But along the way, its energy is captured. In engineering terms, this is called a run of the river design. Its power comes from the Congo River's enormous flow and natural elevation drop without needing to build a dam to raise water levels. This means that per unit of electricity generated, the flooded area and number of displaced people can be reduced by 1 to 2 orders of magnitude compared to traditional dams. Now look at its core, heart, the turbines. Each turbine unit planned for Grand Inga exceeds 700 megawatts. Many countries in the world have national grids that are smaller than that. A single spinning unit can be larger than an entire country's power system. And these turbines will be neatly installed underground, carved directly into solid bedrock to form a subterranean power station. Hiding the machinery inside the mountain not only protects it from flooding and stabilizes temperature, but also greatly improves structural integrity and reduces long-term maintenance costs. Here, the mountain itself becomes part of the machine. In simple terms, the Three Gorges Dam creates its head by brute force concrete construction, while Grand Inga uses existing natural elevation and only redirects and converts it. That changes everything. But that doesn't mean Grand Inga is easy to build. On the contrary, large-scale underground excavation, ultra-precision equipment installation, and unpredictable geological conditions all make it an unprecedented engineering challenge. At this point, many people might ask, if this place is so ideal, why doesn't the local country just build it themselves? To answer that, we have to face the harsh realities along the banks of the Congo River. The Grand Inga Hydropower Project is located in the Democratic Republic of the Congo. This country is home to some of the richest mineral resources on Earth. Cobalt, coltan, copper, diamonds, and gold, many of the strategic minerals that modern civilization depends on, are buried beneath this land. For cobalt alone, an essential material in lithium battery cathodes, the DRC supplies about 70% of the world's production. Yet despite sitting on this massive treasure chest, over 70% of the population in the DRC still does not have reliable access to electricity. Across the African continent as a whole, around 600 million people live either without electricity or with highly unstable power supply. That is nearly twice the population of the United States. This is not a lack of resources. It is a severe lack of infrastructure. In fact, the DRC has over 100,000 megawatts of exploitable hydropower potential, but less than 3% has been developed so far. It is like holding an enormous oil field, but only inserting a single straw to extract it. If the Grand Inga Hydropower Project were fully built and operational, it could theoretically completely overturn this equation. A 40,000 megawatt power source feeding into Africa's regional grid would force a complete recalculation of industrial capacity, mineral processing, and residential electricity supply across multiple countries. This is not just adding another power station, it is effectively plugging 23 Gorges dams worth of energy into the continent's electrical system. But theory is just theory. In Africa, delivering electricity from turbines to end users is often even harder than building the dam itself. Why is transmitting electricity even harder? Think about this. A surging 40,000 megawatts of power would flow out from a single point, while the entire national grid of the DRC is only about 1,000 megawatts. That means the generation capacity is about 40 times the country's entire grid size. If this power stayed within a small domestic grid, it would simply be wasted. The only viable option would be export north toward Egypt, south toward South Africa, and west toward Nigeria. But long-distance transmission is absolutely not as simple as stretching a wire across continents. With traditional AC transmission, a significant portion of energy is lost every few hundred kilometers. To send electricity from the Congo to South Africa, over 3,000 kilometers away, using a sea transmission, you could lose more than 1/3 of the power before it even arrives. The solution is high voltage direct current transmission, or HVDC. This technology allows massive amounts of power to be transmitted over thousands of kilometers with very low energy loss. And HVDC is exactly where China dominates. China is one of the global leaders in this field. China already operates ultra-high voltage direct current corridors exceeding 3,000 kilometers in length. A typical example is the Hami-Fei-Zhengzhou line, about 2,200 kilometers long, which has been operating reliably for years. There is also the Fei 1100K V-Changji-Feiguan line, stretching 3,293 kilometers, one of the highest voltage, highest capacity, and longest distance transmission projects in the world. These are not theoretical papers. They are fully operational infrastructure assets. What does 3,000 kilometers mean? It is roughly the straight line distance from New York to Los Angeles. China is already transmitting electricity stably across that kind of distance domestically. This technology is a prerequisite for absorbing Grand Inga's power output, and it is also one of China's key bargaining chips in the project. If Grand Inga's electricity were sent to South Africa, it would require roughly 3,000 kilometers of ultra-high voltage DC transmission lines. And South Africa's state utility Eskom has been experiencing some of the worst rolling blackouts in its history, with load shedding exceeding 200 days in 2023. A stable, large-scale external power source would be nothing short of a lifeline for South Africa. In fact, the Grand Inga Hydropower Project is not a new concept at all. The first serious engineering studies date back to the 1960s, an era before the Apollo moon landing and before the internet even existed. Engineers standing at Inga Falls calculated numbers that are essentially the same as today's estimates. However, over the next 60 years, only Inga I and Inga I were built, with a combined capacity of just 1,775 megawatts, barely a fraction of the planned 40,000 megawatts. Due to aging equipment, maintenance backlogs, funding shortages, and political instability, these two dams have rarely operated at their design capacity throughout most of their lifespan. By the 2010s, actual output often fell to half of the design capacity, with several turbines shut down for long periods due to lack of spare parts, turning what should have been proof of concept into a cautionary example. This shows that building large-scale infrastructure here is not just about money. It also requires stable governance and long-term maintenance capability. Since gaining independence in 1960, the DRC has experienced civil wars, regional conflicts, and weak institutional capacity. Its biggest financier, the World Bank, publicly withdrew support in 2016, citing governance concerns and questions about electricity distribution. Whether Grand Inga's power would truly benefit Congolese citizens, or mainly serve large mining companies and export markets. Around 70% of the DRC's population lacks access to electricity, while nearby mines operate 24 hours a day. The World Bank's withdrawal left a vacuum, and a vacuum never stays empty for long. China stepped in at a moment when everyone else was stepping back. Why China? Because the Three Gorges Dam was built and operated by China Three Gorges Corporation. This kind of institutional memory doesn't come from reports. It is forged through 20 years of on-site construction experience embedded within the organization. At its peak, more than 30,000 workers were operating simultaneously on the Three Gorges project with a total concrete volume of 28 million cubic meters. At that scale, ensuring quality and safety requires world-class project management, supply chain coordination, and on-site decision-making capability. There is also Power China, which has extensive experience building hydropower stations in remote and challenging environments. At Ethiopia's Gaib hydropower station, they completed a 1,870 megawatt facility in 5 years, one of the largest in East Africa, delivered ahead of schedule and operating reliably. In Bolivia, Laos, and Pakistan, Chinese hydropower companies have accumulated extensive experience delivering large-scale projects under complex geographical and political conditions. All of this is capability built through real-world execution. China's involvement in Grand Inga is structurally different from a typical outsourcing contract. Chinese firms position themselves as lead consortium partners and financiers involved in long-term arrangements spanning construction and operation. When the last turbine is installed, the relationship does not end there. Maintenance contracts, grid integration, and operational upgrades all continue for decades within the same framework. The Export Bank of China and the China Development Bank have also provided financing packages for multiple African projects, with repayment structures often based on future electricity revenue or resource-backed arrangements. This structure effectively locks China into the project for a 20 to 30-year time horizon. At the same time, over the past 2 decades, China has built more than 10,000 kilometers of railways, nearly 100,000 kilometers of roads, and dozens of ports across Africa. Together, they form a real-world network, meaning that when transmission corridors cross multiple sovereign states, China already has a layer of diplomatic and commercial relationships it can draw upon. Grand Inga is not an isolated dam. It is the central node of an entire power grid. And whoever controls a key node in a grid holds a very special kind of power, because when you want to turn on the lights, you have to go through me. If China helps build, finance, connect, and operate Grand Inga, then for decades, any country connected to this grid would maintain continuous institutional ties with China in areas like power dispatch, equipment upgrades, and maintenance services. There is no need to control majority equity in the dam, and no need to station troops in any country. You only need to become the party that can fix things when the system breaks. 40,000 megawatts of power would completely reshape the industrial geography of southern and central Africa. Regions that previously could not host factories due to electricity shortages would suddenly gain access to stable baseload power. Mining and mineral processing could shift from overseas back to local production. Ports, railways, aluminum smelters, and data centers, all energy-intensive infrastructure, would reorganize around reliable, large-scale electricity supply. Currently, over 50% of Africa's minerals are exported in raw form and then refined abroad before being re-imported as finished goods. If electricity costs fall, smelting and refining could remain local, fundamentally transforming the continent's export structure. One detail is important here. The stretch of the Congo River at Inga Falls flows through a gorge and then directly into the Atlantic Ocean, with no downstream countries depending on it for water intake or irrigation. This means Grand Inga would not trigger transboundary water disputes like dams on the Nile River. Technically, the only coordination required would be transit agreements. This condition carries far lower political risk than almost any other major transnational hydropower project in the world. And that is precisely what makes Grand Inga geopolitically clean and extremely attractive. The wheel of historical change has finally turned to the present day. The planned next phase. Inga. I would, if built alone, generate about 4,800 megawatts. And the full Grand Inga scheme, if completed in stages, would ultimately reach 40,000 megawatts. Preliminary design work for Inga has already been completed, bidding is underway, and Chinese companies are among the leading contenders. The entire Grand Inga project is divided into multiple phases, with construction potentially extending into the 2030s and total investment estimated at over $80 billion. Chinese companies view it as a strategic asset, the largest piece of the Belt and Road Initiative's energy puzzle in Africa. An international consortium involving the Congolese government, South Africa's Eskom, and Chinese companies has been negotiating for years over power offtake and transmission corridors. South Africa's aging coal plants are being rapidly phased out, while intermittent renewables cannot meet baseload demand. Grand Inga's stable hydropower is positioned to fill that gap. If completed, 40,000 megawatts would redefine Africa's entire energy landscape. Rolling blackouts in South Africa could end, and mines around the Congo could refine minerals locally. The International Energy Agency estimates that if Grand Inga operates at full capacity, GDP growth in Central and Southern Africa could rise by 1.2 percentage points annually, as electricity shortages have long been the #1 bottleneck to industrialization. But completion remains a very big if. Governance in the DRC cross, border transmission coordination, the security of thousands of kilometers of lines, and long-term maintenance are all challenges, no less complex than building the dam itself. Sustaining reliable operations would also require deep involvement in training local talent and developing supply chains. If China were to simply build and leave, the equipment could quickly fall into disrepair, just like Inga I and Inga II. That is why the Chinese approach has included long-term operational cooperation from the very beginning, both as a commercial logic and as a logic of mutual benefit. When we see headlines in the future saying China is building the world's largest hydropower station in Africa, don't just imagine concrete and turbines. Try instead to imagine a transmission corridor stretching across 3,000 kilometers. Imagine every country along the route having to decide how transit electricity is priced, how their own grids connect, and who holds long-term operational control. Imagine how many of the 600 million people without electricity might ultimately have their lives changed by this flow of power. Grand Inga is an equation. The geological half is simple, the political half is still unsolved. And China has chosen to stand beside this equation, participating in every variable from beginning to end. It does not own the Congo River, but it helps define how the river's energy is allocated. A century from now, if Grand Inga truly operates at 40,000 megawatts, it may be remembered as far more than a hydropower station. It could be the true starting point of African industrialization or the opening move of a very different kind of geopolitical game. Before the lights come on, no one can be sure which one it will be.